Good morning. In this video tutorial we will learn how to use Python to read out the DAQ of the example number 8. In the previous example we developed a firmware that implements a leading edge trigger that fires the acquisition of waveform using the oscilloscope block inside compiler. Our hardware setup is the same of the previous experiment, so the experiment number 8. We have the detector emulator KNDT4800 connected to the CDK board DT1260, and the detector emulator is generating exponential signal. In order to develop the application in Python, we need to open Visual Studio Code on your computer and load the folder that the SciCompiler generated for you, containing the Python example and the Python code. So access to the example ANSK8 that we generate previously. Open the library folder, Python folder, and select the folder. As I explained before, you need to modify in the file functions the path of the DLL if you are using Windows, because Visual Studio Code in Windows does not manage automatically the startup folder. So if you run without enter a full path in the load library, you will not be able to debug your code. So I entered the full path of the DLL, and we can have a look to the file. We have the typical part that is present in all SciCompiler project, that is the low-level function to access to the hardware, and then we have some more extra function. We have the function to set the registers, to set so the threshold, the polarity, and the inhibit of the trigger that we inserted in the firmware. We can open SciCompiler and just to have a recap of the application Note 8 firmware. So we can load. Do you remember there is a trigger leading edge block with 3 registers: threshold, inhibit, and polarity. This register controls the behavior of the trigger, and an oscilloscope. The oscilloscope received the data, the analog data acquired by the ADC, and have 2 digital tracks, one for the trigger, the other for the time over threshold, and the trigger is also connected to the external start of the oscilloscope in order to use the trigger to start the acquisition and the digitizing of the waveform inside the oscilloscope in a synchronous way. So, coming back to Visual Studio Code, we have another set of functions that are used to configure and control and download data from the oscilloscope. We have the start function that starts the acquisition of a waveform, the decimator that is used to set the decimation factor on the oscilloscope in order to overcome the limit of 1000 samples that we set in the waveform length. With this function we can take a sample every n sample, and in this way we can increase the time length that we can explore with our block. So we have also the pre-trigger, that is the function to set the pre-trigger, that is that take the number of samples we want to be stored before the trigger is fired. So we can have a look in the past before the trigger, the trigger level for the embedded trigger, leading edge trigger inside the oscilloscope. The trigger mode function allows us to set on what we want to trigger. So we had this kind of mode. So we have the analog. It means that we will use the internal oscilloscope trigger to trigger on the leading edge of the signal that comes from the specified channel, and the specified channel is selected by the variable that is oscilloscope trigger channel. So if we set channel 0 analog, the value of threshold that we set with the set trigger level will be used to identify the signal inside from the channel 0. We can trigger on digital tracks, we can run in free running, or we can we can run on external trigger. At the end, we have the possibility to specify if we want to look for rising or falling edge of analog signal or digital signal by specify in the variable oscilloscope trigger edge rising or falling. Okay, then we have a function, the get status, that returns if the oscilloscope has a valid samples captured, or it is waiting for a trigger. The get position is a service function that is used to understand where is in the buffer, in the readout buffer, the first samples. Get data is the function to download the data. It takes that argument, just a timeout, that is the maximum time that can be used to wait for the download of the data. The reconstruction data is used to convert the raw data downloaded by the get data function in samples. So it takes the oscilloscope data, that is the data that is captured by the get data function, so the raw data, the oscilloscope position, that is the trigger position, so the value returned by the get position function, and the oscilloscope pre-trigger, that is the value that we set it in the pre-trigger function, so this function. Using these three parameters, using the data and these two parameters, the function is able to reconstruct correctly the waveform captured by the oscilloscope, and it returns the analog signals, the digital and the digital tracks. So have a look to the example file. In the example file, we have the typical part that is related to the connection to the board, and then we have the some variable to set the parameter of the oscilloscope. We can, for example, set the trigger mode, the trigger edge, the trigger channel, the trigger level, and so on. Now the default code generated by the SciCompiler, this is automatically generated by SciCompiler, is configured to run in free running mode. The code just set up the oscilloscope and then wait for a waveform. So in the code forever, we set the decimator, we set the pre-trigger, we set the trigger level, we set the trigger mode, and we start the oscilloscope. We wait forever that the status becomes different of 1, so it means that the acquisition is completed. And when the status is 0, it means that we have, when the status is 1, it means that the acquisition is completed and we can proceed to decode and download the data. So we get the trigger position, we get the raw data, we reconstruct the data, and we use the matplotlib to plot the waveform on your screen. So now, if we run the example, you see the baseline and just the last channels are 0. So we can change the frequency, the rate, in order to have some more waveform inside the screen, and maybe decrease a little the tau. Okay, so this is our signal. Okay, now we are not triggering on anything. We can stop the example and change the trigger on analog, and set a trigger level of 2500 and run again. Okay, as you can see, now we are triggering correctly on the signal that is acquired by the oscilloscope. If we want, we can also change the decimation factor to 10, so we will have a 10 times longer view of the waveform. Okay. At this point, if you want, you can do as exercise. You can use the function to configure the leading edge trigger. So this function to implement the external trigger in the oscilloscope. Thank you. That's all.